Okay, hi, welcome everyone. For once you are here and also for you who are watching this recording, we are very happy to have our sixth webinar in the IMIM community. So today we're going to talk about value generation using data science. It's a very interesting, trendy topic at the moment. So it's related to, I would say, to data, big data, and statistics and of course informatics and how this shapes for business decisions. So we are going to have a small presentation about the IMIM in case that you are new to our IMIM community. Then we're going to present our keynote speaker today, Professor Preciado from Tecnología Monterrey. And then we're going to have some Q&A session and well, some information about our next webinars and where you can watch the recordings of this webinar and our previous other 5 webinars as well. So basically, the outcome for today, after you have watched this webinar or you have attended this webinar, is to know more about how you can use statistical modeling and different computer science approaches for this decision making, and how you can create solutions using data science and the value that you can create for this. So things like pricing optimization, the appliances into Industry 4.0, how to do traffic demand modeling are some of the topics, okay, that we're going to cover today. Of course, our keynote speaker will explain more about this later on. My name is Isaac Limus. I'm a professor at Universidad Politécnica de Madrid in Spain. We are the coordinator institution in this IMIM program with a consortium, which means that we are different universities affiliated to deliver this program. So welcome from our side. And what's the IMIM? So the IMIM is a multi-site program, which means that you get to study in different places. I will show you the mobility later. And the idea is that you get more training into business and managerial skills, okay? So it's very similar to an MBA program, but it has the advantage or the distinction that you also use many engineering background theories behind, so that we're combining, and that's our proposition. We have been recognized by the European Union as one of the Erasmus Mundus labels, which means that this is one of the high quality programs that have been sponsored by the European Commission. And this is the program structure. So you will start learning about management in UPM in Madrid. So things related to strategy, resources to data, accounting, marketing, general introduction to management topics will be here in Universidad Politécnica de Madrid. During the second semester, you will go to our partner in the UK, Watt University, and there you will learn more about projects and operations in the company. And then you can choose for the third semester 4 different options. So one option is that you go to the Dubai campus of Watt University to have a specialization in supply chain management. Another option, if you prefer to go for a specialization in finance, it's Politecnico di Torino in Italy. The third option would be how to do business with China, and our partner is Northwestern Polytechnical University in Xi'an. Or the other option is to have a specialization in data science and innovation, and you can choose any of the 3 campuses from the Tecnológico de Monterrey, either in Mexico City or Guadalajara or Monterrey. So today, actually, our keynote speaker is from this university, the last university, and he's from campus Monterrey. And then the last semester, that is the semester where every student performs their master thesis, they can actually be located everywhere in the world. So we have no limitation here. The only thing is that you need to have a tutor from any of our partner universities, but you can do an internship in a company, or you can do university-based research as well. And this can happen during the 4th semester at any part in the world. So it's very flexible in that sense. Our students come from everywhere, so you can see here, okay, we have representation from all the continents, mainly from Asia and from Europe, okay? So, but now with our new partners, we also expect more representation from the Americas in general. And these are some of the companies where our graduates are working right now. Okay, so if you can see, they are in the top manufacturing and service industries, and also with many top employers. Okay, so if you want to find out more about the IMIM program, or you know somebody who could be interested in this, you can also redirect them to us, and we have more details. Okay. About that in the end, in the last slide of this presentation. Good. So having said that, now I will like to welcome again to Professor Jose Luis Preciado. He is currently the director of the Master in Engineering Management at Tec de Monterrey in the campus in Monterrey. And well, he's going to be our keynote speaker today. So I will give now the floor to him so that he can start with his presentation, please.
Okay, good. So I'll start sharing my screen and we'll start talking about value generation using data science. So let me start sharing that. Okay, and switching to presentation mode now. All right, so today's talk is going to be about, first of all, a little bit of background, okay, on how modern data science came to be, which is something I'm pretty interested in because now I'm doing data science, but I actually had to study other things because there were no data science degrees back when I was studying, which wasn't that long time ago. It was probably 10 years ago or something like that. There were no data science programs. Even I would say 5 years ago, there weren't very many. So you had to be strong in one of the fields that ended up merging or like interacting to create modern data science. So I'm going to give you a little bit of background. It's something I always want to cover in my data science talks because I think it's interesting, and it's also useful because it teaches you what was the train of thought, the different trains of thought that had to collide in order to get to modern data science. Okay, and I precisely talk about that convergence in a couple of slides after talking about the background. After that, being our masters in engineering management programs, more of an applied flavor, I have devoted about half of the talk for case studies. Okay, for some case studies from my own either professional or research experience. Okay, and I explain how to create or how what we have created data science solutions that have been able to add significant values in the context we were applying them. Okay, so well, let's get started with a bit of background. So first of all, statistical modeling has been around since forever, since maybe a couple of centuries, even if you go back to the linear regression model. And it was already widespread before the spawn of modern data science, of course. And some of the most often used tools were generalized linear models, either for regression tasks or for classification tasks. And with generalized linear models, I include, of course, the classical ordinary least squares, like linear regression type of thing. It is a subset of generalized linear models, but also logistic regression, for instance, Poisson regression. And we have actually used Poisson regression in a couple of very modern solutions, and it ended up being the best choice to go. So GLMs are definitely still there. They're alive and kicking, okay, but they have been around for quite a long time, okay? Then another classical problem in statistical modeling is that of density estimation. So why would you want to estimate a density in the first place? Well, it usually comes from the context where you don't have a lot of data. So where this histogram that you're creating out of some observations is not fully reliable in the sense that it doesn't include everything that could have happened, okay, in your population, because you're dealing, because you got it from a sample, pretty much, right? So then we have all this density estimation theory that has been around forever. For instance, MLE, maximum likelihood estimation, is one way of doing it. Bayesian approaches, of course, also exist for this. You have a prior, then you multiply times the likelihood, and you get something proportional to the posterior, right? And just renormalize it, and you can get your posterior density. And the other classical problem in statistical modeling is hypothesis testing, right? So I have two samples from different populations, and I want to show that one particular metric or characteristic is different in one or the other. So if you're thinking about highly applied contexts in management of a management flavor, so this can be maybe sales in two sets of stores that are comparable in every other sense. So they are similar in many of their characteristics. Maybe the kind of city they're located in, maybe the size of the store, maybe the kind of market they serve, and they have maybe similar assortments. Well, that's possibly a candidate for a good hypothesis, good all hypothesis tests, right? Okay, so that has been around forever. Now, what is the context? So what was the context where all these techniques were created? So all these techniques, all these theory came before massive data sets were available, okay? So the context where these models were supposed to take, to be at their full potential, let's say, was a context of scarce data. Okay, so you didn't have a lot of data. In many cases, you had to specially collect it for whatever study you were conducting. Okay, so it's like, hey, I want to show that a pattern exists or a correlation exists. Well, I'm going to collect data for this specific population and just for my very particular study. Okay, because data was expensive to collect. Okay, so if data was expensive to collect, then you want to just do it as much as needed, right? So there was no organic source of data. There was not a source of data that just kept on growing organically because of an infrastructure. Okay. Well, moreover, one other characteristic these models have is that many times they will assume that the data is generated from a specific probability model. Okay, so in the case of OLS, if you want to do, you don't need to assume normality, but if you want to have nicer inference results, sometimes you do assume normality in the residuals and do some model checks against that, for instance. Then speaking about that, there is a strong emphasis in meeting model assumptions. So classically, when you went to school and you learned linear regression or maybe design of experiments or something along that line, where you had to use a linear model, there is a strong focus on those courses to spend a lot of time on residual analysis, right? So essentially, you assumed that these data had specifically the structure described by your GLM. And of course, your GLM or generalized linear model has some parameters you can estimate, right? So in the example of linear regression, you estimate the coefficients. So you estimate some parameters in your GLM. And then after you estimate them, okay, you said, well, this is my model, but I also assumed a lot of things about the residuals. So maybe not a lot of things, but very specific things. It's like maybe you assumed a normal distribution for the residuals, and you need to go and check against that. If you didn't assume a normal distribution, at least something you need for OLS is not having heteroscedasticity, which is different variance, okay? So maybe you do a heteroscedasticity test, right? Or do some plots to check that heteroscedasticity in the residuals is not present. And after doing all these residual analysis and goodness of fit diagnostics, you say, well, data, I cannot show that data doesn't behave like the model I assumed, which is kind of a way to skew things a little bit a little bit to the route where your model works. Okay. So, well, that is, by the way, I adapted this figure from this great paper, which makes these contrasts between this line of thinking and another kind of thinking I'm going to show you in a couple of minutes. Okay. It's called Statistical Modeling, the Two Cultures. Okay, well, now after that, more modern models became available. They are mostly non-parametric in nature. So meaning the objective is not to summarize the information we get from data in a set of parameters anymore, okay? Which was the case in the GLMs, for instance. So here we have highly flexible models that can grow more and more complex the more data you have, okay? So they have very, very high degree of flexibility, a lot of degrees of freedom. Okay, if you want to think about it in that way. So if you think of a GLM, every parameter is a degree of freedom, right? In these non-parametric models, they intrinsically have a very large number of degrees of freedom to actually fit data. Okay, well, so examples of these developments are, of course, decision trees and neural networks. And nowadays, you have decision tree ensembles. Are probably the most popular way to predict structured data. And neural nets, stacked neural nets, which is deep learning, is the most popular way to deal with non-structured data, such as voice, texts, images, and whatever. Okay, so essentially using either decision trees or neural nets in complex ensembles, or in complex ensembles in the case of trees, or in a stacked way in the case of neural networks, is what gives you, what leads you to the state of the art of this kind of modeling. Also, regression. So these are useful for regression and classification tasks, but you then also have unsupervised learning, such as the one that takes place with clustering. So in clustering, you essentially want to group data points that have similar X variables or independent variables. Okay. You want to try to create groups that are distinct from each other. And maybe the most popular algorithm to do this is k-means. Maybe you've heard about it. And finally, so a lot of the tools that develop upon these more modern models can use resampling. So for instance, the very famous random forest algorithm uses heavily the resampling techniques. And an example of that, a resampling plan, is bootstrapping. Okay, so we use bootstrapping to actually get some inference in these more complex models, because in the classical models, you automatically got the inference, right? So even with some equations in some cases. So if you run a linear regression and you're okay with assuming normality, and you see your residuals and they behave, and you don't reject the hypothesis test for normality, well, in that case, you automatically know what the confidence intervals of your prediction are, okay? Just with an equation. Here, in this kind of models, is not nearly as straightforward. You need to resample the data, rerun your model to get some confidence intervals. So it's much more computationally intensive. Okay, and precisely the model context for this kind of models is different. Okay, so these models came to be when we already had a data-rich context. Okay, so we have abundant data now, and if you notice the icon here, this is a database meant to represent the database, while this was meant to represent a single file. Okay. Right, so we have abundant data. This is a data-rich context, and for starters, and something I like a lot, is that we don't assume that our model is right. Okay, so we assume that there is some data generation process. Okay, there is some data generation process, and we are trying to approximate it with these highly flexible non-parametric models. Okay, and the validation here, since we were not assuming the data behaved the way we said it was going to behave, the validation here is of a completely different nature. So here we want to validate by checking whether the predictive error of the models we are coming up with is acceptable. And with acceptable, I mean within the bounds defined by the problem context. And then next, does the interpretation meet basic axioms of the application context? Of course, these models often, especially by people who are using them for the first times or first couple of times, they think of these models as black boxes, or almost, or if they're very optimistic, as gray boxes. But in reality, there's a lot of mining, a lot of pattern mining you can do in these models, and you can extract very, very clear interpretation of what the model is doing, interpretations of what the model is doing. It requires a lot more computational work though, but you can get actually clear interpretations of what's going on the subset of the response surface that you estimated that you care the most about. Okay, so so here, these machine learning models consider the repeated use of estimators. So for instance, if you're doing random forest or gradient boosted trees, you are actually repeatedly fitting trees to your data. They assume that data is generated from an unknown process, and they use an algorithm to estimate the process. Okay, you can, as I said, you can get inference from these algorithms, but you require to heavily resample the data. Okay, so there's a strong emphasis in measuring predictive error and in the interpretability of the model, but this doesn't mean you cannot get formal inference results. Okay, well, at least computational inference results. Okay, guys, so then how are statistics relevant to the case studies I'm going to present? Well, because I will talk about how you can use GLMs for choice models for tollways. So for instance, if you're trying to build a new road that will be the competitor of a currently existing road, and you're planning to charge for that road, or if you want to have a toll lane in an existing freeway, you can estimate, or an existing highway, you can estimate a utility function based on some input data I will discuss about, to create a choice model for those who will select the tollway and who will select the free option. Okay, and with that, you can actually put some value or assign some economic value to actually building the tollway. Okay, all right. We're also going to use time series models, and these are ARIMA models or Box-Jenkins models, to capture seasonality in one of the case studies I'm gonna be talking about. And for price optimization, we're going to estimate price elasticity of demand, again, using either GLMs or the machine learning models I talked about. And finally, we will use something called Pareto Frontier to assess the performance and performance versus quality prediction. Sorry, performance versus quality trade-off of the predictions we're getting. Okay, so all this stuff we just talked about, we're gonna land it down in some of the case studies we're gonna cover in this latter part of this presentation. Okay, that was the learning part. Okay, so that was the background about the learning part. And I know that there's really strong emphasis on this right now. It's like if you go online or in the research communities and whatever, there's a lot of focus on this. But let's not forget about the second half of your data science solution. So the first part of your data science solution is about understanding patterns, extracting patterns from data, understanding how demand behaves, how a particular manufacturing process behaves in the context of an Industry 4.0 solution. Okay, However, once you know the patterns, sometimes it's easy to make decisions based just on those patterns, but sometimes it's hard. And sometimes there are constraints to the decision alternatives you have. And to actually put that in math and be able to put it inside of a solution requires optimization. Okay, so optimization is what allows us to make concrete choices, okay, based on the patterns that we have already learned from the learning algorithms. Okay, so in optimization, the classical techniques are possibly linear programming, nonlinear programming, and integer programming. Of course, you have mixed integer programming, which mixes integers with non-integer variables. Okay, well, so some classical example of optimization applications are transportation problems, where you have some sources of demand and some sources of supply. Okay, and then you want to match them to minimize some sort of transportation cost, maybe. Then you have the generalized resource allocation problem, which comes up in portfolio management. So let's say you have a limited budget, or you have limited space, or you have limited area, and then you want to distribute that budget across different potential projects, okay, or different potential investment alternatives. And it turns out that since it's a discrete choice problem, it's not as simple as just computing the benefit to cost ratio, right? So you actually have some special solution structure because it's an integer program, okay? And it's called the generalized resource allocation problem. And lastly, in a classic manufacturing context, you have the aggregate planning problem, where you're trying to match your workforce and maybe other resources, such as machine time, to your particular demand forecast. Okay, so good. So here are some examples that we will use in our case studies. So for traffic engineering and like for tollway modeling, you solve an optimization problem called user equilibrium. And with that, you can create hopefully a reliable representation of where traffic is going to, of how traffic is going to distribute. Okay. Then for the price optimization case study I will present, we have price optimization considering product substitution. So essentially, if you have a substitutable group of products, how to price the products inside of those groups in such a way that they cannibalize each other the least possible, and that you optimize for either revenue, traffic, or margin, depending on what you're interested in. And finally, in the other case study, we will use the GRAP, or generalized resource allocation problem, to select projects or like production lines in a facility that are the better candidates or the best candidates to have a digital twin. Okay. Okay, cool. So optimization has also been touched by this data science revolution. So classically, you have also a data collection process, or data collection stage, because data collection was relatively expensive in terms of the resources it consumed. Then that led you to some estimation of parameters, because your optimization problems require some parameters to be known. So if you think of a linear program, you need to know the coefficients, let's say the cost coefficients. What is the fixed cost? What is the variable cost of things? And you would need to know what are the rate of resource consumption, okay, of consumption of resources. So these parameters can be either estimated or are known by the business context, and so on and so forth. But these were questions you used to ask once, okay, once every time you run this. And finally, you came up with a solution, and you generated some scenarios, right? So, hey, what would happen if the cost went up by 10%, or if the resource consumption became more efficient and we were able to lower it down a little? Would that change the optimal solution, right? So this is the classic flow for your optimization problem solution. However, now that we have real-time data and that we have massive data stores, well, this is happening more in a cyclical way, okay? So you actually solve the optimization problem with the data that is available at one point in time, but then you refresh the solution, gradually, okay? Not gradually, sorry, periodically. And this periodicity can be actually quite short. So it can be a daily thing. So for some price optimization models, they are refreshing every day. And especially like for online prices. So here you come up with an optimal solution, you post that solution to your website, for instance, and then that leads you into a new data feed for how demand reacted. And then with that data feed of the new demand patterns that you generated by changing the price, maybe some of the parameters change. So maybe that leads you to a re-estimation of your price elasticity of demand function. And then that goes back into your optimization problem. Okay, so this is solving in a very periodic way. And sometimes the periodicity, as I said, can be short. Okay, so this is a transformation that optimization has gone through because of the massive availability of data. Okay, finally, and I have to talk about this, even though none of the case studies are about this, but it's an important thing to mention. In computer science, just like people in statistics and econometrics, we're dealing with quantities, like very specific structured problems. The people in computer science, so computer science communities, were dealing with unstructured problems of an unstructured nature, such as text, images, and voice. So in text, we have what's called natural language processing. In images, we have image recognition. And in voice, we have speech recognition. So people in the computer science community were dealing more with this kind of problems. And nowadays, deep learning is the state of the art, we would say. And the usual metric for this kind of problem, since there's no structure you need to comply with in this kind of a problem. So if you think of an econometric problem, you want your demand function at least to be monotonic, if not monotonic and convex, right? Not monotonic and concave, depending. So in econometric problems, in problems of that nature, the nature of problems that the statistics communities and the optimization people were dealing with, those problems were of very structured nature. Here, the solution doesn't need to have a particular structure. So deep learning has provided a great degree of flexibility and also of pre-processing flexibility, okay, of this raw data in order to turn it into a useful solution, okay? So in other words, in econometrics, when you create a new variable, it usually has to mean something. It needs to have that very concrete context specific meaning, okay? Here, you can create all sorts of features. And if you have an algorithm that does it automatically for you, like deep learning, well, the better. Cool. Finally, let's talk about the convergence then of these trains of thought, or these research bodies of knowledge, and how they came to be together, just one thing, and allow us to build modern data science solutions. Okay, so one key aspect that happened in this revolution were the breakthroughs in computing power. Okay, so now you could estimate these highly complex non-parametric estimators, and moreover, you could do it with large volumes of data, and moreover, you could do it repeatedly in order to get inference out of them. Okay. Also, the algorithms or the estimators have become more and more efficient. So personally, I have worked on non-parametric convex or concave, if you want to see it that way, regression algorithms. And these algorithms were advancing more and more to essentially accommodate more data and to run quicker. So of course, advances in data storage capabilities have also allowed us to do this, because now you can have databases that are cloud stored and that you can pull from in a reliable way. And finally, and something I really want to highlight, is the democratization of solutions through open source libraries. So a few years ago, if you wanted to code something like a Markov chain Monte Carlo algorithm, you had to do it yourself. And you had to know some very specific concepts about what you were doing, and you had to be really sure and really knowledgeable about every step you were conducting. But now you have these libraries coded by experts, and you can use, you can be 1 degree closer to an user and 1 degree less of a developer, which helps you, which have helped the spread of these solutions. Okay. Okay, so let me see how I'm doing on time. How am I doing, Isaac? Do I have like 5 minutes or 10 minutes?
Yes, I mean, you have 5-10 minutes.
Okay, cool. It will take me about 10. All right, so well, then finally, we have an increased rate of data collection, pattern learning, and solution updating to better suit our changing environments. Okay, so now we have this context of abundant data, and then we have, and that is, and these abundant data are linked to these highly flexible non-parametric models for pattern learning. And then these patterns are fed into optimization models for decision-making. And once those decisions are made, the responses or the changes that the data generation process suffered are again stored in this abundant or big data sets. Okay, so now it has come full cycle, and there is communication across these 3 links. Okay. Moreover, if you build a solution so all of this is on the background, all of this is the back end. If you build the front end to that through, let's say, you create an app with a user interface, okay, that can allow some of the preferences. Let's say you don't care about sales anymore, and you care more about margin for a particular product category, or the cost of some input changes, okay, or there's a new business rule of some sort, then these user interfaces can allow users to actually modify what is allowable, especially in the optimization program, okay, in such a way that solutions that are constrained in a different way are now available. Okay, so let's not forget about the front end, because that's another great feature we have available now. So with this front end, you can alter what's happening here and have some input into your final solution. Moreover, you can have a user interface to actually approve or disapprove what the engine is coming up with. Okay. So here at the very end, you also have the user validating the decision this system or this engine made, and updating policies and priorities. Okay, so this is how your modern data science solution looks like. And it's highly complex. They take a bit to actually come to be, but this is how they look, and it's pretty cool. Okay, let's go over some case studies quickly. So the first of them, it's really close to my heart. This was the kind of stuff I was doing at Home Depot's Innovation Lab a couple of years ago. So price optimization in retail. We have several sources of data. We have point of sales data, so essentially what's in the stores or what is in the website. So all these records of sales and the conditions in which these sales came to be. So what was the price, if there was a discount, what day was it, on what month, okay, on which store did it happen, and in the case of online data, what did they click before or something, or things along that line. And you also have data from the product catalog, And from the product catalog, essentially, to see which products were available in the assortment of a specific store, for instance, or which products are substitutable with other products. Then you have macroeconomic data. So you have macroeconomic data in the sense that, well, can we expect demographics in one region to be the same as in a different region? Does it make sense to have different demand estimations? Okay. And then we have, of course, user-defined policies and business rules. Okay. All of that is put together in cloud computing and, sorry, in a cloud-based storage, and our solution will use cloud computing afterwards. Okay, so we use machine learning or statistical learning to estimate the demand and price elasticity functions, and also to conduct cluster analysis for outlier detection. And once we come up with the solution we think makes sense in terms of the prices, then we usually conduct pilots, and we do A/B testing. And this has to do with hypothesis testing, to build a control group, a test group, and see if the treatment or the price changes we suggested made sense. Okay. Then lastly, sometimes we're not able to come up with a control group. So what we do is using time series analysis to extract the pattern before we conducted the test and use that as a counterfactual. So pretty much, if we had done nothing, this model describes what would have happened, and here is what actually happened. Okay. Okay, cool. So how does optimization come into place in price optimization in retail? Well, as I have mentioned a couple of times already, we have some substitutable product groups, and you want to optimize the revenue that you get from the group as a whole. Okay. And we use mixed integer programming. And the cool thing again is that all of this takes place in a single Python solution. So you have some Python code doing the learning and using the GLMs or the non-parametric models. And in a different function, you have the optimization happening also in Python. Okay, so you don't need to have anymore these separate solvers for optimization problems and this separate software for estimating statistical models. You can do everything in one solution, okay, and in the same language, which is really convenient. Okay, so we use this data science convergence concept here in the sense that we were able to build apps to recommend prices and assortment changes. And we were able to build online apps that track the A/B testing, the A/B tests we were conducting. And then the user can say, well, this A/B test is going terribly in this market, so let's shut it off and go back to the previous price. And in the case of price recommendations, you can actually approve or disapprove recommendations from the engine. Okay, now the most recent one I have worked on is predictive defect detection in an Industry 4.0 context. So this might sound like as extremely different from the previous case study, but it's actually not. So only the data sources are different, I would say, and also the fact that instead of having economic theory as your source of constraints and your source of structure for the solution in the other problem, in the case study number 1, here we have physics and metallurgical knowledge as a constraint source. Okay, so essentially whatever solution you come up with, it needs to make sense to the experts. Okay, and it has to come from actionable sources. Okay, so actionable parts of the process, and it needs not to come from variables that are results of other variables. And that's why you need to incorporate expert knowledge in this case. So, well, in this case, the data is based on 2 sources. The first source are sensors. Okay, so we have a highly sensorized manufacturing process. In this case, it was steel galvanizing. And You also have data from visual inspections. So essentially data is coming into the databases as well as it's being punched by some operators. Okay, so two sources of data, mostly from sensors. I would say 99% of data from sensors or 95% of data from sensors, and the remaining data from visual inspections. And so what did we do here? We had to actually use machine learning models for regression and classification to try to find defects in products. And some of these defects are of a discrete nature. They either happen or don't happen. And some other of these defects happen against a threshold or what do they call this? Specification limit. So you have to predict this continuous quantity. And if this continuous quantity goes above the upper specification limit or goes below the lower specification limit, then it's a defect. Okay, so sometimes, so for some of these properties of the materials, we use regression models and for some other properties or defects, we used classification models. Okay, now if you have a very mature process like steel galvanizing, well, it happens that you have a really pronounced imbalance in the data set. So maybe you can have defect rates that are below 1%. So below 1% of your data is defective and the other 99% is not defective. So we actually had to tailor heavily the algorithms to be able to extract signal from here, from this kind of pattern. And in the same sense, we also had to create some ad hoc dimensionality reduction algorithms that work in this highly imbalanced context and with the kind of goals the company had. So in this case, this company was most interested in minimizing the the false negative rate. So they wanted to catch all the defects, and then as a secondary objective, they wanted to produce the smallest number of false positives they could. Okay. So in this, let's say, goal programming context, so a multi-objective optimization kind of context, we had to also link the dimensionality reduction strategy to that, which is kind of cool. Okay, so after we came up, we came up with a surface of different solutions, which build a Pareto frontier, if you want to call it that way, because that's the way I call it at least. And these frontiers described the trade-off between false positive rates and false negative rates that we got out of the different model configurations. And from these model configurations, of course, we want to select one of them. So it is partly expert knowledge, and partly we can use it. Partly we can do it using portfolio management optimization, like the one we do with generalized resource allocation problems. So essentially, if for a particular production line, we're able to achieve a reasonable solution, and for another one, we're not able to achieve not such a reasonable solution, even if the second one is most valuable, in terms of the potential income, you have to weigh how good your prediction is versus how much or how valuable is the correct defects on that production line, put this into an optimization problem and get a discrete set of the production lines where it would be priority to have a digital twin, okay? Okay, so finally, how does the final solution work? And this has been recently implemented already. So we have an online model execution, which is feeding real time with both the setup values of the parameters, and the setup values of the parameters are before the process starts. Okay, so before the process starts, you know that a particular type of steel roll is coming into the process, and you also know that you have put some configurations or settings into the different equipment, pieces of equipment along the process. Okay, so the first thing you want to answer is this configuration of parameters good for the kind of a product I'm trying to make? Okay, or will it lead to an increased defect rate? If that is the case, even at the very start of the production line, we can recommend to tweak the parameters specifications for the line in order to reduce the probability that the product ends up being defective. Okay. All right. Lastly, and I think I'm going to have to jump over this one because I'm out of time, and I actually have to wrap it up. But this is something I used to work a longer time ago, and it is about estimating the demand for a road that doesn't, for a toll road that doesn't yet exist. So the gist here is, the gist of the problem is that you want to build a discrete choice model and try to assess whether your markets, your different markets, either individual users or cargo, are going to use the tollway or not going to use it, and how much they're willing to pay for it. So you solve this problem, called the user equilibrium model to conduct a traffic assignment and roughly assess how the traffic would be distributed. And well, the new thing about this is that now, since we have data from devices and that data is cloud store as well, you can create a solution that also follows this cyclical pattern where you're getting new information, and then maybe you can set dynamic pricing for your tollways. Okay, and this pricing will change at different times of day and on the different days of the week, for instance. Okay. Oh, I love this in Spanish, but it says questions. So, well, it's Q&A time. Please feel free. I just have about 5 minutes because I need to jump into another meeting, but Q&A time.
Well, I don't want to take much of your time. I wanted to ask if there is like a Bible for data science, as I'm starting this bootcamp on data science. So if you recommend anyone in English or in Spanish, as you wish. And the second thing I'm asking, because I have some background on statistics, and I would ask about, just if you have like a quick answer over reliability, and which tools can we use?
Okay.
Like, in a general way, please.
So first about the bootcamp, then I'll talk about the reliability stuff. So about the bootcamp, it's usually a good way to kickstart yourself and to know what is out there in terms of the tools you could use. Okay. But in reality, I wouldn't. So once you're done with your first bootcamp, so I would say two sources. So library documentation, and the cool thing about library documentation is that if you check the sources for the library documentation, you can also go one step back and check on the ideas that generated those algorithms and models that are now implemented in the libraries. And another very important source that we must not forget about are actual books on the topic, because sometimes people just rely on posts. Okay. And that's okay if you have a specific question on how to do something. And however, I think bodies of knowledge need to make sense. Okay, so you need to always operate in a context where, so knowing a broader context, knowing the more complete context of what you're doing. So let's not forget about that. There are many cool books about deep learning. So you have one by Francois Cholet called Deep Learning with Python, for example. So that's one valuable source. So yeah, once you're done with the bootcamp, make sure to check out library documentation, library examples, which are very rich, for instance, for sklearn, which is one of the main libraries we use. And also, let's not forget the bit more formal bodies of knowledge, such as literature. Okay, thank you. And about reliability, I'm not a reliability guy, not a quality guy. So
okay, so
really don't know what's the deal there.
Okay, no worries. Thank you so much.
Okay, no problem.
So do we have any other question, perhaps? I just have one that we were asked during the registrations. So some people were asking about the difference, because they hear big data, deep learning, statistics, machine learning, and I mean, is there any difference? Business intelligence, that was also there.
Yeah, of course.
So could you explain a little bit, I mean, the differences, or how can we use them in business?
Okay, cool. Yeah, so I'll give you some boundaries, okay? So first of all, let's say AI, artificial intelligence, is essentially extracting patterns or making decisions using something you coded, pretty much, okay? And inside of that, you can even think of optimization as AI, right? Because you're making decisions in an artificial way. And you can think about learning patterns also as AI, right? Okay, so cool. So we got that down. Now, inside of statistical learning, you can call statistical learning the process where you have an algorithm to gain some inference, okay? So statistical learning is a term that someone from the statistics community would call it, because they care about the inference, and I care about the inference. I'm one of those. If you only care about the prediction, or you care mostly just about the prediction, that is more of from the computer science background, and that is where the machine learning term comes from. Okay, so essentially you're using so from the point of view of computer science people, you're using a learning algorithm that extracts rules from the data, pretty much. If you want to think about it as a statistician, you're using an algorithm, and you can play some inference around the results of that algorithm. Okay, so that is what we could call either machine learning or statistical learning. Okay, now business intelligence, that is already into a more applied context. That can include some use of statistical models, but usually it's more about understanding the broader patterns that are happening, and it's also heavily towards the building of dashboard type tools. Okay, dashboard type tools, heavier on the visualization emphasis. So I would say that. And advanced statistics versus machine learning, it's only about where the algorithms came to be. But now, as I said during the talk, you can use them to approximate an unknown data generation process. So that is the way in which they have blended.
Okay. Thank you very much, Jose Luis, for the answer and also for the presentation. It was very interesting, also the cases that you have been working with. So I'm sure, I mean, we will leave your details so that people can contact you perhaps
Okay, cool.
Other questions, and also after watching the webinars. So thank you once again. Just as a closure, I would like to share this. So these are our next webinars, okay? So of course, in the newsletter where we're gonna send the link to the recording for this webinar, we will also send the invitation for the next events. Here you can also look at the YouTube channel of ENUPM. So we have a playlist there with all the different webinars and so forth and so on. And well, other than that, thank you very much. If you have further questions as well about the IMIM and the webinars and all these activities, you can also send us an email here. And thank you very much, Professor Preciado, and all our guests here. And thank you for your questions and your participation. And basically, I think that's it. Okay.
Okay, take care. Bye-bye. Need to take off.
Thank you very much. Bye-bye, guys.